Hi, welcome back. In this video, we're going to be talking about the laws of exponents for multiplication and laws of exponents for division. We're going to combine all of these rules and do examples that incorporate both properties. So if you're not yet comfortable with the properties of multiplication or properties of division, I strongly recommend that you go watch those videos first, get comfortable with those laws so that you can get rolling with these examples where it combines them all together. And if you have not subscribed so yet, please go ahead and do so right now. Click the subscribe button so you have more access to videos like these. Let's get started. Before we begin, we're going to do a quick review of the laws of exponents that we've covered already, multiplication and division. If you look at the top left-hand corner, whenever we are multiplying, we want to make sure that we add the exponents. And whenever we're dividing, we're going to subtract the exponents. We always subtract numerator minus denominator. That's supposed to be an x. X minus y. Now, if you look here on the left side, whenever you have an exponent raised to another exponent, we call this power of a power property. This is the power rule. I like to call this as the distributive property of exponents, because we're going to be multiplying this exponent on the outside towards the inside, and we're going to have a to the x times y. As you can see below, we also have, even if we have multiple objects inside the parentheses raised to another exponent, we distribute the x into both of those bases. So we can easily say a to the x times b to the x. Notice how both terms inside the parentheses were raised to the x power as we distribute those two as exponents. Whenever we are dividing and we're subtracting the numerator minus the denominator, we will sometimes get a negative exponent, especially if the denominator is greater. So whenever you have a negative exponent and you want to make sure you change this to a positive exponent, we're going to do the reciprocal. Right now we have a to the negative x, technically over 1. And a to the negative x is in the numerator. So to change this to positive, we're going to do the reciprocal. 1 over a to the x. Notice how a to the x is now in the denominator. So if we wanted to change a negative exponent, you're going to want to flip it by putting in the denominator. If we have a negative, let's do this. Let's say that we have 1 over a to the negative x. To make this a positive exponent, we're going to take it from the denominator and switch it over to the numerator. So it can go from denominator to numerator or from numerator to denominator. Our goal in the end is to have a positive exponent. So you're just going to want to flip it. And then finally, sometimes when you subtract the exponents, they are the exact same exponents. If you subtract them, you can get a 0 as an exponent. So anything to the 0 power is really just going to be, okay? So our goal is to follow all of these rules and these next few examples to get comfortable when to use them, how to use them, and in what order. Let's get started. As we're getting started with these next examples, I strongly recommend that you have a paper and pencil to write this down. Looking at it, you're going to be able to absorb some information, but writing it down with me, pausing the video, trying these examples together will definitely help you absorb the information better. Now, as I begin, this is the idea that I want to follow. I want to make sure that as I'm simplifying all these expressions, that I want to follow PEMDAS, the order of operations. Okay, so I'm going to walk you through how to use PEMDAS whenever you're seeing an example like this. I first start with parentheses. I want to look anything inside the parentheses. Can I simplify anything inside any one of those parentheses? And the answer is no so far. I cannot combine any like terms here or here. And then I want to look at exponents. Do I have any exponents on top of these exponents? Anything right outside of it, out here? And the answer is also no. So I can also skip this step. The next step is multiplication and division. And this is exactly where we're starting. These parentheses around 3m to the negative 2n to the fourth, this parentheses times this parentheses really means multiplication. So we're going to be multiplying all of these terms together. And what I want to do first is I'm going to organize these by grouping them with like terms. I can rewrite them, since everything's being multiplied together, I can write this as 3 times negative 4 for the coefficients. I can write times m to the negative 2 times m to the 6. So I can group the m's together. And then lastly, I can group, I'll do this in a different color. I can group the n's together by saying n to the fourth times n to the negative 7. Now that everything's grouped together by like terms, I can actually combine things and simplify. So 3 times negative 4 simplifies down to just negative 12. M to the negative 2 power times m to the 6. Whenever we're multiplying, we want to add the exponents. So negative 2 plus 6 is 4. So we say times m to the fourth. And then lastly, when we're adding the exponents of n, we have 4 plus negative 7, giving you negative 3, times n to the negative 3. Now that I've grouped everything through multiplication, I don't have any division or any addition and subtraction, but I do have a negative exponent right here. And I want to make sure that for this to be fully simplified, I do not want to have any negative exponents. Technically, everything right now could be written as over 1. So what I'm going to do is I'm going to take this negative exponent and make it positive by flipping it to the denominator. And this is what I'm going to be left with. I have negative 12 times m to the fourth power divided by n to the third power. Notice how it goes from being in the numerator to now being in the denominator. And technically we have a 1 down here, so we can say 1 times n cubed. And this is everything fully simplified. I can't combine anything else. I can't simplify m or n or anything else. And that would be my solution. Okay, as we begin this next example, I want to make sure that I follow PEMDAS as my order of operations. So I'm going to write it here on the side. As I begin, notice how there are no parentheses anywhere in this problem. So I can skip this piece, and there's no exponents outside of those, right? There's no power rule, which means I'm going to start with multiplication and division. As I look at the top, in the numerator, notice how I cannot multiply anything at the top. I cannot combine any like terms. And same with the denominator. I cannot multiply anything in the bottom because there are no like terms. So I'm actually going to start with just the division properties. So let's look at these coefficients. I have 27 divided by 3. The numbers are always like terms. The x's are like terms. The y's are like terms. And there's only one z down here. So there's no like terms with z. But that's how we decided to group them. 27 divided by 3 is simply going to be just 9. As we look at the x's, if we remember, the quotient rule says that when we're dividing, we want to make sure that we are subtracting the exponents for the like terms. So we have negative 2 minus 5. If you're not necessarily great with negatives, put that on the calculator. Negative 2 minus 5 is negative 7. So I can simply say x to the negative 7 power. Then I look at the y's. Again, when you're combining like terms through division, we subtract the exponents. So 6 minus 2 equals 4. And I can say y to the 4th power. And then in the end, we just have a z over here on its own. I cannot combine it with anything on the top. And as we said before, the zero property of exponents, z to the 0 power, anything to the 0 power, except for 0, is going to give us 1. So in the bottom, I really just have 1 for the z to the 0 power. That represents 1. Now, it looks like I've combined everything possible already. The only thing that I am noticing is that I do have a negative exponent. Remember, we want to deal with only positive exponents. So, to get rid of this negative, we're going to take this entire x to the negative 7 and flip it to the denominator to make it positive. And this is our end result. We still have a 9 on top. We still have y to the 4th on top. But now I have x to the positive 7 in the denominator. And that's really it. We have no negatives. I'm done with my division properties, and there's no addition and subtraction. So we're done. Let's try another one. In these next few examples, these examples might seem like they're quite complex because there's more going on, right? There's more parentheses, there's more exponents, they look more difficult. I want to make sure that we follow the same thought process we have been for the last two examples. PEMDAS as our order of operations. So before we begin, I will follow the same system. Parentheses, exponents, multiplication and division, and addition and subtraction at the very end. I want to follow this same order of operations because if I can follow these steps in order, no matter how complex these examples are, they're always going to simplify to something simple if we focus on one step at a time. So let's start with parentheses. Inside these parentheses, can I combine any like terms? And the answer is no. I cannot combine anything in here or in here. So I do not do parentheses. The next thing I want to deal with is exponents. And this is what we mean by exponents. Whenever you have an exponent like x squared, or anything in here raised to another exponent, this is the exponent rule. We're going to be using power up to the power property, which says we're going to distribute that 2 into every term inside. This is the only one that is being raised a power to another power, an exponent to another exponent. So before I begin, I want to make sure I remember that everything inside the parentheses already has an exponent. 3 could be rewritten as 3 to the 1 power. X squared is to the 2nd power, and y alone can also be written as y to the 1 power. Whenever you have a term by itself, I'm trying to write the 1 here. Whenever you have a term by itself, you can assume that it's being raised to the 1 power. I can't get that 1 there where I want it. So I'm going to distribute that 2 on the outside into every one of those exponents. I'm going to multiply the 2 times the 1, 2 times the 2, and 2 times the 1. Let's start with the first term. I'm going to leave that negative 1 on the outside. There's technically here a negative 1. I'm going to write it as negative 1. And inside, or by distributing, I have 3 to the 2nd power. Because 2 times 1 is 2. So now we have, instead of saying 3 to the 1 power, we're going to have 3 to the 2nd power. So I can say times 3 to the 2nd power. I distribute the 2 with the 2. 2 times 2 is 4. Times x to the 4th power. And lastly, 2 times 1 is 2. So we can say times y to the 2nd power. I have simplified everything inside the parentheses raised to another power by distributing into those exponents. And we have these terms. On the back, I do not have any exponents outside of these exponents, so I can just copy this as is in the back. I'm going to write this in red so that you can see that we're really just multiplying times 4 times x, and I can even give this as an exponent to the 1 times y to the second power. And then underneath, there are no more exponents raised to other exponents, and I'm just going to write them as is. Six times x to the 1 and y to the 3. So we are done with this property of exponents. This is known as the power rule, when you multiply by distributing into the exponents. Now I'm going to deal with multiplication. Okay, this multiplication property, I'm going to combine all of these like terms. Okay, so what I have here is I have negative 1 times 3 squared times 4. These are going to be our like terms. Right? I'm going to circle these so that we can see what we're working with first. Negative 1 times 3 squared times 4. You can put that in your calculator, or you can see that 3 squared is 3 times 3, which is 9. 9 times negative 1 is negative 9. Negative 9 times 4 is negative 36. So I'm going to write this as negative 36. And that gives me this, this, and this. I just combined the coefficients. Now I'm going to combine the x's on the numerator because I'm multiplying. When I'm multiplying x to the 4th times x to the 1, remember we add the exponents. So we have 4 plus 1. And that leaves me with x to the 5th power. 4 plus 1 is 5. And that eliminates these. It combines those terms. And lastly, in the top, I'm left with y squared times y squared. And again, I'm going to add the exponents. So I want to write this as y to the 4th power in the numerator. 2 plus 2 equals 4. And that combines these terms. Now that I've combined everything on the top, I go to the bottom. I notice that I cannot combine anything on the bottom. And I'm just going to write the bottom as is. Divided by 6 times x to the 1 power times y to the 3rd power. So we just completed multiplication by adding the exponents with the variables that were like terms. Now we're going to go into division. And to divide, we're going to focus with the like terms of the numbers, the x's, and the y's. So negative 36 divided by 6 comes down to just negative 6. I'm going to write this over here. As I start looking at the x's, x to the 5th divided by x to the 1. Remember, when you're dividing, you subtract the exponents. So 5 minus 1 is just 4. So 5 minus 1 is going to leave us with x to the 4 power. And then for the y's, we have 4 minus 3 is also going to be just y to the 1 power. Or just 1y. I don't have any negative exponents here. I cannot simplify any further. And this is going to be our simplified solution. And just like that, we took this very complex looking kind of example that had a whole lot going on, right? A ton of parentheses, a lot of exponents, a lot of negatives, and came down to just 3 terms. If you follow the steps of PEMDAS and do one rule at a time, things will be simple. And you'll be able to simplify one step at a time. A lot of people like to go from here to the very end in their head. And they're like, I don't know how to do it all together. It's like, you don't have to. You just have to follow one step at a time. And in the process, notice how slowly we get to the very simplest form of the situation. Before we begin this example, I want to encourage you to give this one a try. Why don't you write down PEMDAS and see how far you can go? Press pause, give it a try, press play, and see how we can do this together. Let's get started. So I want to write my order of operations, PEMDAS, parentheses, exponents, multiplication. Bottom. So I'm going to skip that part. Then I want to go to exponents. Notice how I do have exponents raised to another exponent. And here's the same. All of these are being raised to the second power. When you have exponents raised to another exponent, we're going to be dealing with the power rule. So remember, as we begin, you can assume that everything that's by itself is raised to the 1 power. 2 to the 1, b to the 1, 3 to the 1, a to the 1. All of them are raised to the 1 power. That'll help me with the distributive property or multiplication of exponents rule. So I'm going to distribute this 4 into that exponent. 4 times 1 is 4. So I can write 2 to the 4th power. Similarly, 4 times 3 is 12. So I can say a to the 12th power. And then 4 times 1 is 4. So I can say times b to the 4th power. This is the numerator. In the denominator, I'm going to do something very similar. I have 2 is 2. So I can say 3 to the 2nd power. 2 times 1 is 2. So I can say times a to the 2nd power. And 2 times 4 is 8. So times c to the 8th power. And then lastly, here in the back, nothing here is being raised to another exponent. So I just copy it down as I see it. Times 4 times a to the 5th times b to the 1, because there's only one b. Now I want to follow multiplication and division. As I start to multiply, there's nothing on the top that I can combine like terms with, but I can simplify this 2 to the 4th. You can always put this in your calculator, or you can think of it as 2 times 2 times 2 times 2, which is the same as 16. So 2 to the 4th is really just 16. A to the 12, b to the 4. And the bottom, I want to combine like terms. So I have this is a number, and this is a number. 3 squared is really just 3 times 3, which is 9. And 9 times 4 is 36. You can also just put 3 squared times 4 in your calculator, and you will get 36. Now I want to combine the a's. I have a squared and a to the 5th. Remember, when you're multiplying, you want to add the exponents. So 2 plus 5 is 7. So I have a to the 7th power. Because there's only one b down here, I cannot combine it with anything on the bottom, so I just write it as b to the 1 power. And same thing with the c. There's only one c in the denominator, so I copy this as c to the 8th. You see how it's slowly starting to shrink and reduce in size as we're doing these problems? Just gotta take one step at a time. Now I want to get into division. Again, when you're dividing, divide numbers with numbers, a's with a's, b's with b's, and there's only one c. So what do 16 and 36 have in common? They're both divisible by 4. So I want to divide 16 divided by 4. I get 4. And 36 divided by 4, I get 9. So I can just write this as 4/9. Then I want to look at the a's. When I'm dividing, remember, I want to subtract the exponents. So 12 minus 7 is 5. So I have a to the 5th power. How do I know to put it on top? Well, Notice how I would have 12 A's. If I were to do this in expanded form, I would have A times A times A times A 12 different times. And then 7 of those in the bottom. Since there's more A's on top, when I start canceling the A's, I'm going to be left with more on the top. So when you're subtracting, wherever you have more of, that's what's going to remain. 12 minus 7, 5. And because there's more on top, I'm going to leave the 5 on top. And now the b's. To combine those, I do 4 minus 1, which is 3. So I times b to the third. And again, the b is going to go on top because there's more b's in the numerator. And then lastly, there's only one c, and it's in the bottom, and we leave it where it is. As I continue, notice how I cannot simplify anything anymore. Oops. There it is. As I continue, notice how I cannot simplify this anymore. I cannot combine anything, any more A's, any more B's, or any more C's, and I don't have any negative exponents. That is our simplified version of all of that. One step at a time, guys, and you'll get to the simplest form. Let's try one last one. For this final example, I'm going to split this into two different ways of solving this. And then I'm going to show you which one is a faster route that I recommend you to approach. Okay, so I'm going to draw a line down the middle, and I'm going to separate this into two parts. On the left, I will follow PEMDAS, as we have been so far. So I'm going to write PEMDAS over here, P, E, M, D, A, and S. I'm going to start with the parentheses. I'm going to solve everything within the parentheses. Can I simplify anything inside the parentheses? The answer is yes. I have a to the 1 and b to the 1 over here. So as I'm dividing, remember that when you divide, you subtract the exponents. 1 minus 5 is negative 4. So inside the parentheses, I have a to the negative 4. That cancels the a values, combines them to that. And then on the b's, I have 3 minus 1, which is positive 2. And all of this is being raised to the 0 power. I was able to simplify inside the parentheses. Now I'm going to deal with this exponent on the outside. Remember that when you're raising exponents to another exponent, you're going to multiply the exponents or distribute with the exponents. So as I distribute, I have 0 times negative 4, which is a, well, the parentheses is going to go away, a to the 0, and 0 times 2 is also 0. If we remember, anything to the 0 power means that a to the 0 is really just going to be 1, and b to the 0 is also going to be 1. And 1 times 1 equals 1. So this whole thing just equals 1. Now, as I'm starting these problems, and I notice on this other side, I want to solve it separately, I do notice that this the entire parentheses is being raised to the 0 power. So before I even begin to simplify what's inside the parentheses, everything inside the parentheses, whatever that is raised to the 0 power. And as we discussed with the 0 property rule, anything to the 0 will be equal to 1. So it doesn't really matter what's inside, because everything in here to the 0 power just equals 1. And notice how they both equal 1. So to save all of this work that we did on the left, to save all of these steps for PEMDAS, just notice how everything is being raised to the 0 power. So everything within the parentheses will just equal 1. All right, guys, I hope this has helped. Please let me know if you have any questions. Don't forget to subscribe and like the button if this has helped you in any way. And as always, we'll calculate later.